Hi, I'm Charlie Thompson, and this is the too long didn't read version of the Chapter 4 lecture slides, the introduction to atmospheric water and weather. And I was just looking at the title and thought, I think the title of this chapter is great, because if it was just weather, that would downplay the role of water in weather. So the key to weather is water, so atmospheric water and weather, that's a good title for this chapter. What are we going to talk about? Well, it's a huge chapter, so I'm going to divide it up into 2 weeks of weather fun. The first week, we're going to talk about water's unique properties, humidity, which is water vapor in the atmosphere, atmospheric stability, and clouds and fog. So this week, we're talking about water's unique properties, water vapor in the atmosphere, atmospheric stability, clouds, and fog. Next week, we'll tackle air masses, processes that lift air, mid-latitude cyclones, weather forecasting, thunderstorms, tornadoes, and finally, tropical cyclones. So the most important concept, how does water behave in the atmosphere? Well, it evaporates and absorbs heat. It condenses and releases heat. It freezes. It melts. What are the forces that produce our weather? The most important force is going to be the latent heat of condensation. When water vapor condenses, it releases heat that warms the air, which makes it rise, which makes it expand, which makes it cool. And if you get condensation, it releases heat. So the latent heat of condensation is going to be the most important force that produces weather. What causes violent storms? The latent heat of condensation. So we'll have to spend a lot of time about the concept of the latent heat of condensation. I don't think you can really appreciate, understand, enjoy weather until you understand the latent heat of condensation. So water's unique properties. Water is really weird. It's the only substance that occurs on Earth at normal temperatures as a solid and a liquid and a gas. It also has the highest specific heat of any common substance. So specific heat is how much energy it takes to change the temperature of a substance, and water has an extremely high specific heat. Phase changes occur when water changes from one state to another. As water changes from one state to another, latent heat is absorbed or released. And it's time for vocabulary words. So water exists as a gas, just like oxygen and nitrogen. It exists as a gas in the atmosphere. There's also droplets of water that exist in the atmosphere. We see them as clouds. And water is also a solid ice. So evaporation and condensation, when liquid becomes a gas, it evaporates. When a gas becomes a liquid, it condenses. When a liquid freezes, it becomes solid. When a solid becomes liquid, it melts. Hopefully everybody's good with those terms. But there's also this third type of thing that happens with water, that water can go right from being a solid to a gas or a gas to a solid. So it doesn't have to condense into a liquid and then freeze. It just goes right from being a gas to a solid. And you might have seen this with dry ice. If you've ever seen a chunk of dry ice out on a table, the dry ice will sublimate. It goes right from being a solid to a gas. It doesn't melt, so you have a puddle of carbon dioxide that then evaporates. It goes right from a solid to a gas. And water vapor deposits and becomes ice. You might have seen this in your freezer as frost. This is how you get those crystals of ice in the bags of food in the freezer. It's when the water vapor deposits, becomes a solid directly. So for ice to become liquid, it has to absorb heat. And at that phase change, it doesn't change temperature. If you put 80 calories into a gram of ice at 0 degrees, you're going to have water at 0 degrees. It absorbed heat, and the effect of that is it changed its phase. Once the phase has been changed, then you can increase the temperature. So if you added 100 calories, you'd get it up to 100 Celsius. And as you keep adding heat energy to that gram of water at 100 Celsius, nothing's going to happen until it evaporates. That's the phase change. 540 calories of heat applied to a gram of water at 100 Celsius, you're going to end up with water vapor at 100 Celsius. So the temperature didn't change. The phase or state changed. And then once it's water vapor, if you keep adding heat, it'll change its temperature. And the opposite happens when water vapor condenses. When it goes from water vapor, a gas, to liquid water, water droplets, it's going to release 540 calories for every gram that condenses. Same thing happens with ice. To freeze ice, 80 calories have to be released. So if you have a gram of water at 0 degrees and you pull 80 calories out of it, you're going to have ice at 0 degrees. So the temperature doesn't change. It just magically goes from a liquid to a solid, and heat is released. So condensation, heat is released. Freezing, heat is released. Humidity is just water vapor in the atmosphere. Humidity is water vapor in the atmosphere. How much you can have is a function of temperature. The higher the temperature, the more energy is available to evaporate water. So this is a chart of maximum specific humidity, which is the maximum, the most grams of water per kilogram of air that you could have at any temperature. It doesn't mean you have that water vapor. It's just, this is how much energy there is. There's enough energy at 0 degrees to evaporate 4 grams of water. At 10, it's 8. At 20, it's about 15. At 30, it's about 27. And finally, at 40 degrees, you can have 47 grams of water vapor, which is pretty close to 2 ounces of water per kilogram of air. So again, this is the maximum. It doesn't mean that you have that much. This is just how much you could have at any one temperature. This is one of the ways that we're going to measure humidity. Another is relative humidity, and relative humidity is how much you have. In this case, we have 4 grams, and the max at this temperature is also 4 grams, so the relative humidity is 100%. So as temperature changes during the day, relative humidities can change even if the specific humidities don't. Specific humidity, it's just expressed how many grams per kilogram do I have. So if it got warmer by 10 degrees, the maximum would double. So now at 11 o'clock, we can have 8 grams. We didn't magically get more water vapor, so we still have 4 grams. We have 4, we could have 8, so the relative humidity has dropped to 50%. The specific humidity stays the same all day long, 4 grams, 4 grams, 4 grams. But the relative changes as the temperature goes up, relative humidity goes down. If it gets warmer by another 10 degrees, and now the maximum is 16 grams of water vapor, that's how much you could have. I still have 4 grams. The most we can have is 16, so now the relative humidity has dropped to 25%. So meteorologists will tell us what the relative humidity is, but they don't really pay a lot of attention because it changes so much. With temperature, like this plot from the Sac Airport, the coldest time of day has the highest relative humidity because the coldest part of the day has the lowest maximum specific humidity. The warmest part of the day would then have the highest maximum specific, so you'd expect to see the lowest relative humidity at the warmest part of the day. Atmospheric stability is the key to rain. Stability is the tendency of an air parcel to rise. If it rises, it's going to cool and we get rain. Remain in place or fall, we don't care about. Hot air balloons are a good example of this. They rise because they are warmer than the air around them. We'll talk about clouds and fog. We will discuss Luke Howard's cloud classification system. He divided clouds into 4 categories: high clouds made of ice crystals, mid-level clouds, low-level clouds, and puffy clouds. And clouds are super important to understanding what's going on in the atmosphere. For example, if you see cumulus clouds, you know that it's going to be nice weather. It's not going to rain. If they get bigger and bigger, then a thunderstorm is coming. You should go inside. If you see cirrus clouds that become cirrostratus and altostratus and then stratus, you know that a warm front is moving in. So looking at the clouds can tell you a lot about what's going on with the atmosphere, which is why we'll spend time talking about what the different clouds look like, why they look that way. They don't just look that way for a reason. Like these high clouds are made of ice crystals, so you get these cool halos. We'll talk about cumulonimbus clouds, the big thunderstorms. We'll talk about hail and lightning and thunder. We'll talk about lenticular clouds, which tell you the atmosphere is incredibly stable. We'll talk about types of fog and how those different types of fog are formed. Fog is basically just a cloud on the ground, so you need warm, moist air, and then something makes it cold, like a cold ocean, advection fog. Cold air, you got your evaporation fog. Valley fog, we'll talk about all those. We'll talk about radiation fog. I hate talking about radiation fog. We'll talk about rain and snow and the mechanisms, collision, coalescence, the Bergeron-Finn-Dyson process that cause rainfall. We'll talk about hole punch clouds and how differential maximum humidities allow them to occur. We'll talk about snowflakes and how humidity and temperature combine to form different patterns of snowflakes that then produce different effects in the atmosphere based on how large they are. We'll talk about all those sundogs and arcs. We'll talk about virga. We'll talk about air masses, and air masses are huge blobs of air, roughly the size of continents. They extend up through half the thickness of the atmosphere. Air masses move around and bump into each other and make weather. And as they move around, they gradually change. For example, if you had really cold, dry air. Oh, perfect. If you had this cold, dry air moving across the Great Lakes, which are big bodies of open water, that dry air is going to pick up moisture. As the air cools, you're going to have the water vapor condensing, and you'll have clouds and snow. This is called lake effect snow. So downwind of the Great Lakes, there's way more snow than upwind. Like you can see, there's virtually no snow there. Oh, hey, Chicago. But then on the downwind side, lots and lots of snow. We'll talk about processes that lift air, which is going to be incredibly important. If you want to make it rain, you need to lift air up. That's the key to rain. That's how you make it rain, kids. You lift air up. So we'll talk about convection as a mechanism that makes rain. We'll talk about orographic lifting, where the air gets lifted by a mountain up. And on the other side, the air sinks and gets heated up and makes Chinook winds. These were important in kicking off the fires in Oregon in September 2020. These downslope winds, as they move downslope, they get compressed, they get heated up, they're hot, they're dry, they're very powerful. And so those really fanned the flames of the 2020 outburst or outbreak of fires in Oregon. We'll talk about how that relates to rain in California, where the two patterns that produce rain are high latitude, because you're under the polar front. Down here in Southern California, we're more under the subtropical high, so droughty, rainy. So high latitude and high altitude. You can see the Coast Range and you can see the Sierra Nevadas, which then explains why you've got deserts in Nevada, which is also totally fascinating because as I've mentioned before, and I'll just keep saying, 95% of everything that we'll talk about is just because of latitude. And the other 5%, it's going to be plate tectonics. So in this case, the main driver of precip patterns in California is going to be latitude, followed by altitude. And the altitude is a function of plate tectonics, because that's what's created the mountains of the Sierra Nevada, the Cascades, the Klamaths, all those mountains. So before the uplift of the Sierra Nevadas, this rain would not have been caught by the Sierras, and it would have fallen across Nevada. So Nevada, 30 million years ago or so, would have been much wetter. Just fascinating to think about. The idea that shifting continents and rising mountain ranges are going to affect climatic weather. Continental scale weather, rather. We'll talk about warm fronts and cold fronts as lifting mechanisms, and how those combine to make mid-latitude cyclones, these continent-sized storms made up of a warm front and a cold front spiraling counterclockwise around a center of low pressure. We'll talk about weather forecasting. We'll look at weather forecasting instruments. We'll look at weather forecasting computers. We'll talk about Doppler radar and how important it is in tornadoes and rainfall analysis. We'll talk about violent weather, so thunderstorms and derechos, which were again in the news in September of 2020, a derecho outbreak across the Midwest, unless it was August. Whatever, August, September. Tornadoes and tropical cyclones, the largest, most powerful storms on Earth. So we'll talk about lightning. We'll talk about derechos. Very similar to this is from a bunch of years ago. I think this is from 2014, 2015. And it's a time series of these winds sweeping across the East Coast, going all the way from Illinois and Michigan, all the way to Maryland over the course, from 2 o'clock till midnight. So over 10 hours running across the entire East Coast pretty much. That was a derecho. We'll talk about tornadoes. We'll talk about tropical cyclones. Talk about sea surface temperatures and how they relate to cyclones. We'll talk about storm surge and the effects of tropical cyclones. And we'll watch this video, or you'll watch it. I've seen it a dozen times. It's a great video. It's 27 storms, Arlene to Zeta, about the 2005 hurricane season in the Atlantic. And the 2005 hurricane season was the first year ever that we ran out of names. The National Weather Service has lists of names years in advance, so you could go online and see what the 2024 fall storm lineup names are. And when they run out of I think it's 21 names, when they run out of those names, they go to Greek letters: alpha, beta, delta, gamma, epsilon, zeta. So in 2005, they ran out of names. The 2005 hurricane season, instead of ending in November with the official end of the season, there were storms into January. So the 2005 hurricane season, instead of ending in November, actually ended in January 2006. It'll be interesting to see when the 2020 hurricane season ends, given that I think we're up to beta already and it's only September. Man, what a chapter. It's one of my favorites. I hope you really enjoy the chapter on weather. I think once you understand it, it makes it all so much more fascinating. Anyway, that's it for the Too Long Didn't Read for Chapter 4. I hope you enjoy it.